Good afternoon, everybody. Welcome to sunny but cool Thursday afternoon of Chem 170 Organic Chemistry with your host, me, Dr. White. All right, here's the game plan for today. First of all, I'll mention a couple of things. Then we'll go through problem set on the alkanes. I was going to say two. One, it's actually chapter 2. I don't really follow the chapters. It's the alkanes and hydrocarbons. And then what we'll do is go back to the alkenes and alkynes, the fun part, reactions. And then after that, there'll be time for the distillation lab. And that's nice too. All right, before I get going, a couple of things. Don't forget there's a lab due today. If you get in a little late, that's okay. But if you don't hand it in, you're going to lose a lot of points over the semester. They're easy points. Oops, I shouldn't have said that. But I don't ask for a whole 20 pages of lab report or anything like that. My lab reports, if you follow my introduction and read it and watch any videos associated with it, should take you about 15 minutes or less to answer the questions. If you're slow, you want to take your time, maybe 20 minutes. All right, that's one thing. The other thing I want to ask is, do you happen to cook with natural gas, like on your stove or in your oven? And did you think about that natural gas is methane? It's an alkane. Did you happen to, thank you, Nana. Did you happen to drive by a gas station and you think about half the weight of the gasoline they're selling are alkanes? Or did you look at a candle and did you happen to think about half the weight of a candle are alkanes? Remember, organic chemistry is all around you. I stole that from SpongeBob. But anyways, and it won't hurt you to think about it when you're not in my class or in our Zoom class. All right, let's get going. Remember, there's no such thing as a dumb question in my class. And I should warn you, I don't know about warn you, tell you, that even with my speakers, or if I were in a class, I'd be saying, even with my hearing aids on, one of the hardest things for me to pick up is letters of the alphabet. So if you ask a letter by turning on your speaker, I may ask you to repeat it once or twice, or say something like B boy, because when it's a word, if I hear most of it, I know what it is, but a letter, you only get one shot. All right. All right, everybody see on your screen, thumbs up, people. Alkanes practice problems, the answers. Thank you. All right, now, number one, and the way I do problem sets is I'll do one page at a time. And if you have any questions about what I did, ask. If you want me to do another one on that page, ask, because I don't read minds, especially over Zoom or in face-to-face. All right, number one, this is an important skill. How many carbon atoms are in the longest chain of the following? And how do you do that? Notice I was really nice. I didn't even put any hydrogens to confuse you. See what a nice person I am? And if we look at B, count the carbons. C, that's carbon, 1, 2, 3, 4, 5, 6. Now, if we look at D, you have to look at all the possibilities. And one would be across 1, 2, 3, 4, 5, 6. Remember, we're looking for the longest chain, and a chain means linked together, carbons bonded. And a chain doesn't have to be straight. You can move it all around. Well, same thing with carbon atoms. And if we look, there's another chain, 1, 2, 3, 4. Then down here is 5 and 6. And they're both the same, so the longest chain is 6. Now, if we look at F, now Dr. White got sneaky. And what's the longest chain? Well, if you count across 1, 2, 3, 4, and I don't have it written there, but 5, 6, that's one chain. But a chain doesn't have to be straight. It can zigzag. 1, 2, 3, 4. Now 4 is bond to 5, 5 is bond to 6, 6 is bond to 7, 7 to 8, 8 to 9. And that's why the longest chain is 9, not 6 across. And if you went up to this carbon here and called it 1, it would still be 9. All right, that's an important skill. Time out for a public service announcement from your host, me, Dr. White. Remember the first day of class, I talked about riding a bicycle. And if you didn't know how to ride a bicycle, and I gave you that really, really good, well-made Blu-ray, how to ride a bicycle. And for next month, you studied that hour after hour. What's going to happen the first time you get on a bicycle? Fall off. With practice, you get to learn how to ride a bicycle. Watching me do the problems or the examples I do during the lecture is just like watching that Blu-ray, except I'm probably better. No, anyways, organic chemistry is more fun than learning how to ride a bicycle, but I'm biased. I'm an organic chemist. But watching me is like that. You have to try it on your own. And that's why I created the practice problems. Don't look at the answers first. Try it and then look at the answers. And if you have problems, come to me for help. I'm available. Ask during class, ask after class, come to my office hours. And then a public service announcement. And this public service announcement was brought to you by me. Uh-oh, it's really bad humor Thursday. All right, next, give the IUPAC names for the following molecules. Well, first of all, you have to find out what's the longest chain. And if we look at B, it's 1, 2, 3, 4, 5, 6. And then I hope you have learned this chart. If not, you should know this by Monday. Well, you don't have to, but if you want to do good on test number 1, you should. And 6, IUPAC name for alkanes, 6 is hexane. If we come over here, that's the name of that, hexane. Now, if you look at C where it says or, on my test, until we get into fats and oils, I will never use the paren like I have after the or. Ooh, another public service announcement. This is a public service announcement day. All right, listen carefully. Test number 1, which is coming up soon, historically has the highest average. Not always, but I'd say 9 out of 10 semesters I've taught, like majority, it does. And what that means is it's the one easiest to get the most points on. And your grade is determined by total points. So you should study like you need every point for every test, but especially test number 1, you should practice because that's the one to get the easiest points if you practice. And I will be honest, I've had students who've done very poorly on test number 1, then they turn it around, but their road is a little harder to a good grade. So study, do the practice problems. All right, let's look at D. What's the IUPAC name for D? And what you have to do is find the longest chain, and either way you count, it's 4. And I counted across, you can start here, 1, 2, 3, 4. And that's spoken form, 4 carbons. You've learned this table, hint, is butane. Now we have something left over. Remember, that's called substituent. And this substituent is an alkyl group, has 1 carbon, CH3. And hopefully you've learned this chart, hopefully, hint, and that's a methyl group. Your old friend. And what carbon is it on? We count in such a way only from the ends of the molecule, not starting anywhere else. That's a common mistake on test number 1. And I'm telling you that so you don't make it. And you count in such a way from either end that all the substituents get the lowest number. Well, here we go 1, 2. If we went the other way, 1, 2, 3. I hope you all know 2 is smaller than 3, so it's 2-methylbutane. And I wanted to show you E, molecules can rotate. And notice, oh, this is different. No, it's the same thing. All I've done is rotated 180 degrees like I just did. And guess what? It has the same name, 2-methylbutane. Now, let's look at, let's do G. And G, the longest chain here, I was being nice, I don't have to, across is 9 carbons. And that's the longest chain. And if we look at this table, which you hopefully have learned, 9 carbons is nonane. Well, and guess what I just did? I didn't want to do that. And now, once we have nonane, the straight carbons here are spoken for, and we have 2 alkyl groups left over. CH3, you know, is a methyl group. Now let's look at this one. 3 carbons, and notice the center carbon is bonded to our chain. And if you look at the key alkyl groups, 3 carbons, the center carbon is bonded to chain. That's called an isopropyl group. Dr. White loves isopropyl, also tert-butyl. They've been good to me, I've been good to them. And if we go back, that's an isopropyl group. Now we count. And if you count from the left, in this case, the methyl group is on 2, the isopropyl is on 4. Now, here's why I'm not holding you to the IUPAC alphabet rule. Prefixes you forget. So when you're looking at which goes first by alphabetical priority, methyl group is M, isopropyl group is P, not the I, because that's a prefix. And I have 2-methyl, 4-isopropyl nonane. Now, if you'd written down 4-isopropyl, 2-methyl nonane, I would give you full credit. Don't tell the IUPAC, please. By the way, there's no IUPAC, but it sounds nice. All right, let's look at H. A ring. How many carbons are in the ring? You count every bend in a line. And if we count, there's 6 of them. 1, 2, 3, 4, 5, 6. Now, if this were an alkane, 6 carbons, hexane. Now, it's a ring, so you have hexane, but you have to add the prefix, that's the thing that goes in the front, cyclo. Common mistake on test number 1, students forget to put the cyclo. And guess what I do? I mark it totally wrong, because that's not hexane, that's cyclohexane. Now, when you have one alkyl group on a ring, no matter where it is, that's always going to be carbon number 1. And because everybody knows that, we do not put a number down for where the alkyl group is when there's only one alkyl group on a ring. And in this case, what do we have? Oh, 6-membered ring, cyclohexane, and 3 carbons. Center carbon is attached. I know that's an isopropyl group. So that's isopropyl cyclohexane. Now, I always tell them, don't call now. It's my dentist office. And I'll let my answer machine pick it up. One more. Stop. Ooh, it listens. Didn't listen to me. Now stop. Thank you. All right, let's look at K. What do we have? Ooh, a ring. How many carbons? 1, 2, 3, 4, 5. And 5-carbon alkane is pentane. Now, since it's a ring, it's cyclopentane. I ran out of room, which is why I wrote it underneath, which you can too on the test. And what do we have on that ring? A tert-butyl group and an ethyl group. 2 carbons ethyl, 3 carbons bond to the center carbon, bond to the ring, tert-butyl. Let's go and look at it, see if I was right. 2 carbons ethyl. 4 carbons, 3 bonded to the center carbon, bonded to the ring, and that's the tert-butyl, or later on next week, I'll be a lazy organic chemist, just call it T-butyl. You can call either one. Now, IUPAC rules, which I try and always follow, is the group with the higher alphabetical priority, closer to the front of the alphabet, comes first. Now, tert-butyl, the tert you ignore. So that's a B and the other one is an E. So the highest priority gets the number 1, and you number in the direction clockwise or counterclockwise to give the rest of the alkyl groups the lowest numbers. In this case, clockwise gives ethyl 2. If you went the other way, it'd be 1, 2, 3, 4, 5. And which is smaller? High math time now, 2 or 5. Hopefully you pick 2. And therefore, this is 1 tert-butyl, 2 ethyl cyclopentane. But since I'm not going to hold you to that rule, there are 3 other answers I would accept. Don't tell anybody else. And that would be if you had the name switch, you had the number switch, you had the names and numbers switch. So those would all be correct. I should point out, when I grade tests, I'm not sitting there like saying, ooh, how many points can I take off? I'm sitting there saying, I hope they get it right. Can I mark it right? And if it's wrong, I'll give you a mark it wrong, but I'm trying to, and hopefully pulling that you do it right. All right, the other 2 types of nomenclature questions that will be on test number 1. The first one is, give, or I might say draw, the IUPAC name for, or not draw, give the IUPAC name for the following molecules. The other type of nomenclature question, also known as skill, is draw the condensed structure for the following IUPAC names of molecules. And here again, you have to know the alkanes right here and this table also. Now, the other thing you have to know is how many bonds to carbon? 4. How many bonds to carbon? 4. Hold on, I got to fix that finger someday. 4 bonds to carbon. That has the same problem. There we go. 4 bonds to carbon. 4, 4, 4. So methane, no other bonds, so it has 4 hydrogens. And again, butanes, 4 carbons, put in the hydrogen. Now let's look at C. How do you decode this? And unfortunately, on this machine, I'll have to check if I can do it. I can't write on a PDF file with my tablet yet. But anyways, 2-methylpentane, you start from the right, move left, from the right, move left, pentane 5 carbons, and carbon 2 is the methyl group CH3. You could have put it on this carbon, which had also been 2. Now, if we look at F, we have 2,3-dimethyl hexane. And here we have, going from the right to left, hexane. You've learned this table, hexane, 6 carbons. 6 carbons. Ooh, methyl, I know that, CH3. Oh, di. Di is a prefix meaning 2, tri means 3. Di 2, tri 3. This is di. So there are 2 methyl groups, and notice I have 2 numbers in front, and that tells me they're on carbons 2 and 3. Now, I made a mistake on right here, big mistake, totally. Yes, I make mistakes too. And it should read 1-tert-butyl 2-ethyl cyclopentane, but even with the wrong name, you should be able to draw it correctly. Start from the right, move left, cyclopentane. Pentane, 5 carbons, cyclo, it's in a ring, 1, 2, 3, 4, 5. And I do it this way to confuse you, but I'll show you how most of you have drawn it. And on carbon 1, any one of these carbons, you can put a T-butyl group, tert-butyl. And the second carbon over here on this side, you can put a ethyl group. Now, let me show you how most of you probably would have drawn this. Oh, look out, I'm having a good ring drawing day. And I have my tert-butyl group. And I know how to put in the hydrogens because they're 4 bonds to carbon. We don't show hydrogens on a ring. If this is 1, you probably called this 2. And an ethyl group is 2 carbons, and there it is. Oh, look, it's your old friend propane. Now, on test 1, about 45% of the 45 points will be reaction product questions. And they are, give the reaction product or products for the following reaction. And the first one is we have CH3, CH2, CH4, oh, that's propane, oxygen. And how do you do that? Well, let me show you. And you look at this molecule and say, what's different or how can I identify it? Well, it's only got carbon and hydrogens. It's an alkane or a hydrocarbon. It's only got carbon-carbon single bonds. That makes it an alkane. I'm reacting with O2, oxygen gas, and this could have been a cycloalkane. And when you react that, you know this general reaction, you get carbon dioxide plus water. Now, those are the chemical products. You also get heat, but for this class, that's all we're interested in. Therefore, this is an alkane, this is oxygen. You're going to get this. And that's how you do it. And I have to highly stress, you need to memorize this. And how do you do that? Write it down and say it 5 times. Alkane, or cycloalkane plus oxygen gives you CO2 and H2O. Hopefully you know that's water. And you do it another time. And by the 5th time, you'll remember it. And a couple of days later, do it another couple of times, and it'll be burned up here or over here, somewhere up there. I hear a question about to happen. Someone have a question or accidentally put on your microphone? I guess not. I'm always ready for a question. Hope I didn't scare anybody.
Well, actually,
Boris, go for it.
yeah. Where do you post these videos, like these recordings?
What? Say that. When do I post?
Where do you post these videos?
I mentioned it yesterday, but I'll mention it again. That on Tuesday, Thursday, since I don't have office hours, right after I finish, it'll take me about a half hour to process it, maybe 45 minutes. Then, depending how busy YouTube is, and it can be very busy or slow, or not busy, It takes about, for this length, it's a long video, 2 hours and about 40 minutes. It takes about an hour to upload, 30 minutes, an hour to upload, depending, not my internet speed, but YouTube, how busy it is. And then it takes a little longer after that for YouTube to process it. So generally, unless I also, if something happens in my personal life and I get sidetracked, and that can happen, I usually will have it in YouTube by 9:30 tonight or a lot earlier. And sometimes it may be tomorrow morning, but I shoot for, before I go to bed, I'll have it. I guess.
Okay,
Okay,
sounds good. Thank you.
you're welcome. And as always, all questions are good questions. All right, let's get back to the last part of the problem set. Now, if you notice, I have B, what's that? And I shouldn't have put it in parentheses, but this is an alkane oxygen. Guess what? Same general reaction, same product. And C, you get this product. It's a ring, cycloalkane. Oxygen, guess what? Combustion, you get CO2 and water. And just so you can have some fun too, whoa. Here's one for you to try. Give the product or products for the following reaction. 3 points each. Oh, in about a week or so, you'll understand why I do this. That's not what I wanted. That's not what I wanted. Did I tell you today is National Students Turn On Your Webcam Day for Dr. White? Does that work? Shucks. Nope. All right, let's do this. Now, this is a chemistry instructor's favorite trick on a test in organic chemistry. Put a big, scary molecule. But if you know what it isn't scary. And if we look at this, oh, I've got a ring and carbon hydrogens and carbon-carbon single bonds here. This is a cycloalkane. A substituted, meaning there are things on the ring. And it could have been an alkane, which is not. If you react it with oxygen, you've learned this general reaction where you know to put down carbon dioxide plus water, CO2, H2O. And therefore, this is this. Therefore, this is what I'm going to get. Remember, we don't balance the equations in this class. It's a waste of time. You don't have to. All right. And that's problem set 1. Are there any questions? Remember to look down the bottom of my chat. I always forget to do that when I'm on Zoom. Going once, going twice, done. By the way, years ago, I used to go, unfortunately passed away 2 summers ago, sad. But anyways, I used to go with my brother-in-law to different auctions. At that time, he and his father owned a very large bindery company. They bound books and other things, and also folded things, the folding company. You know those little things you get when you get some sort of medicine or anything that's 20 pages all folded up? Their company did that. Anyways, we'd go to auctions for other companies that were being sold, and he'd tell me, keep your hands in your pocket, don't say anything, or you just bought $50,000 piece of equipment. And he'd buy stuff for his company, but the auctions were there, and I'll do that going once, twice, so on. All right, enough of my past. It's time to get to some good stuff. And yesterday, near the end of our lecture, we started talking about, about reactions of double bonds. And the first one I just started talking about was hydrogenation. I'll never ask you what's the name of a reaction, but I will use it. Now I have it drawn this way. Remember, R is like X and Y in math. This is something with carbons and hydrogens. So that means really this is a way of writing any molecule that can even be connected. And here, if we react it with hydrogen gas, H2, and a catalyst is something that speeds up a reaction, makes it go quicker, but is not consumed, used up. And here the catalyst can be platinum, palladium, or nickel. Now, as I mentioned yesterday, a double bond, and you should know this, hint, has one pi bond and one sigma bond. And pi bonds I can break like that. Sigma bonds you don't break other than combustion. In other words, for this class, you're not going to break them. And but the pi bond, if I break it, there'll only be one bond between the two carbons. And hydrogenation, each carbon gets a hydrogen. And this is another general reaction you should know. Hint. And in real life, by knowing these reactions, and later on in a couple of lectures, I'll talk about how these are very helpful to organic chemists. But let's look at the following. And the question is, give the organic product or products for, and A was this molecule plus hydrogen and palladium. And when we put things above and below the arrow, that's just an organic chemist way of being lazy instead of putting this plus that and that. So how do you do that? How do you find out what are the products? You look at the molecule and you say, what's different? What's not a carbon-carbon single bond or carbon or hydrogen atom? And that should get your attention like this. Did that get your attention? And I've got a double bond right here. And everything else is just going to come along for the ride. It won't be affected by this reaction. And I'm reacting hydrogen. And what's palladium? It's a catalyst. And remember, the catalyst can be platinum, palladium, which is in our case, or nickel. And remember, this has one pi bond and one sigma bond. And you can, well, that's awful looking sigma. Still awful looking, but anyways, you break the pi bond, not the sigma, and each carbon of the double bond gets a hydrogen. And one of your friends for test 1, 2, 3, 4 in the final is, do you break carbon-carbon single bonds? And the answer is no. So if we start out with 4 carbons, we're going to end up with 4 carbons. Now, here are my 2 carbons of the double bond, which are these 2. Notice I broke the pi bond. There's only one line between these 2 molecule or carbon atoms. And then, because I know this general reaction, each one of those gets a hydrogen. And now I know there are 4 bonds to carbon, and I can put in the rest of the hydrogens. Now, you can write it this way, which is easier for you on a test. And, oh, I forgot. Well, I think I'll do it. I'll time out for, and I'll put out an email. I just remembered, how will I do it? Next Monday, at the end of class, I will, and it's optional, you don't have to stick around, take about 10, 12 minutes. I will teach you how to eliminate test anxiety and any other type of anxiety, like if you're going for an interview or other things, this works too. And I will cut it out of the, I like the special effects, cut it out of the video, because I don't want it floating around the internet. Someday maybe I'll sell it, maybe, but I still hope. But that'll be next Monday. So make sure you come by. If you can't come by, come to my office hours or ask me when I can do it another time for you. Wrong one. Right one. Now, what I wanted to say, I should have said, is you can write it this way, or notice this carbon right here has this hydrogen, that's 2. So you could also write it. Same thing here, 1, 2, and then this. Either way are identical in my mind. The top way is just easier for you. And that's how you do it. Now, I'm gonna let you have some fun. Your turn. Give the organic product or products for the following. 3 points each. You're doing sophisticated organic chemistry. Now, hopefully it doesn't hurt. It better not. And if you finish early, please be patient. I try and give everybody time to finish. So finish, no. I'm looking up here with a clock with second hands, not hands, numbers. I guess that's the second hand. Oh, it's totally awful bad humor Thursday. Uh-huh. All right, looks like everybody's done, so I'm gonna get to work. So how do you determine what's the product or products of this reaction? Well, you look at the molecule and say, what's different? What's not a carbon-carbon single bond or carbon or hydrogen atom? In a couple weeks, you'll be having nightmares hearing me say that. I hope not, but it's that important. And if we look at what's different, we have a double bond, nothing else. The rest are just carbon, hydrogen, carbon-carbon single bonds. And immediately all I think about is this. What am I reacting that double bond with? Hydrogen. What's nickel? A catalyst. Remember, the catalyst can be platinum, palladium, or nickel. In this case, we have nickel. What happens? Remember, you have one pi bond and one sigma bond. That's a better sigma. And you break the pi bond, and each carbon of the double bond gets a hydrogen. Do you break carbon-carbon single bonds? No. So I have here 3 carbons with a methyl. Guess what? I'm going to end up with 3 carbons and a methyl. Think about it. A week ago, would you know what I'm talking about when I said methyl? See, you're learning. And notice between these 2 carbons, I broke one of the bonds, the pi bond. And now to each one, I'm going to add a hydrogen. And now I know there are 4 bonds to carbon, and I can put in the rest of the hydrogens. Now, one thing, I don't know, it's a convention. I don't know if it's written down somewhere, but I've never seen an organic chemist, myself included, do something like this. Usually you put it top and bottom. If you were to do this on a test, I look at it and say, ooh, that's interesting. And I say, yeah, but it's right. And I give you credit, but oops. This is the way I'll do that. And you could have put the H here too. And that's how you do it. And that's the beauty. And truly, in my mind, it's beautiful and powerful of knowing these general reactions. Because no matter what molecule I have, when I have a double bond, carbon-carbon double bond, reacting with hydrogen and a catalyst, this is going to happen. In fact, I did those reactions in industry, both in a lab and in a chemical plant I supervised. All right, let me do one, and then your turn. And the question is, give the organic product or products are the following. And if we look here, what's different? Well, I got a ring, but that's really just carbon atoms, hydrogen atoms, and carbon-carbon single bonds. But wait, we've got a double bond. And a double bond, and we're reacting with hydrogen and platinum is a catalyst. Remember, the catalysts are platinum, palladium, or nickel. And you break the pi bond, which I did. Each one of the carbons of the double bond gets a hydrogen. Now, in a ring, we don't show hydrogen. So how would I do that? Let's find out. If we look at these 2 carbons, how many hydrogens are in there? Count the bonds. 1, 2, 3. 4 minus 3 would be 1 hydrogen. 1. Same thing here, 1. Let's look at these carbons. How many bonds are there? 1, 2. 4 minus 2 is 2. So you've gone from 1 to 2, same thing here. So you have added it. Remember, on a ring, when you break a pi bond and add hydrogens, you don't show it. Your turn. Give the organic product or products for the following reaction. I'm watching the seconds go by. All right, I think everybody's done. Let me get to work. And if we look here, what's different in this molecule? What's not a carbon? Carbon single bond or carbon hydrogen atom. Remember, every bend of line is a carbon. Oh, look, a double bond. And what am I reacting it with? Hydrogen and a catalyst. That's what platinum is. And catalyst can be platinum, palladium, or nickel. In this case, it's platinum. And remember, double bond has a pi bond and 1 sigma bond. Well, it's a nice sigma. Anyways, you break the pi bond between these 2 carbons, 1 line now, and each one gets a hydrogen. Well, do you break carbon-carbon single bonds? No. So you're still going to have the ring, still going to have the methyl group on the ring, and these 2 carbons are these 2. I broke the pi bond, and you don't show hydrogens, and I'm done. Now, let me remind you, when you take the test, say this was a problem, you don't have to write this underneath. Some of my best students have, some of my best students haven't, but they've all learned this. And that's how you hydrogenate a double bond. Oh my goodness, I went a whole minute over. I'm sorry. Let's take a break. Let's take a break and come back at 2:56. And I'll see you in 5 minutes. I can get up and stretch. Time to get going again. Welcome back. All right, so the first addition reaction I just talked about is hydrogenation. And that's where you're adding hydrogen to double bond. And I've done this in amounts as large as 40,000 pounds, where I supervised it in a chemical plant. And just to remind you, if you have seen the trucks that deliver gasoline to a gas station, those are called tank wagons, and they're standardized. I'll never ask on a test, but it's still something I think you should know because it's interesting. And they're standardized. They're always 5,000 gallons, which comes to, for organic molecules and water too, even 40,000 pounds. And I've done reactions on one full of those, not in the truck or the tank wagon, but in a reactor, and I'll teach you about that. All right, time to do our second addition reaction. Now, this one is where you take halogen gas, X2. In organic chemistry, X are the halogens: fluorine, chlorine, bromine, and iodine. And these are what X stands for, capital X. Excuse me. And those are the halogens. And they exist as a diatomic molecule, X2. So if you have any double bond and react with fluorine, chlorine, bromine, or iodine, what happens is, let's look this way. Remember, a double bond, one pi bond, one sigma bond. Ooh, that was a pretty sigma. And if you react it with halogen gas, and here you don't need a catalyst because the thermodynamics involved is something I don't teach in this class, but I know. And you break the pi bond, and each carbon of the double bond gets a halogen. Now, one of the questions you should ask is, why do you want to do that? Well, it turns out in molecules, when you replace hydrogens with halogens or just add halogens, you make it more flame retardant. And this is a way to make flame retardant chemicals. And one important use of flame retardant chemicals is children's clothing. And before the government a number of years ago and the organic chemists developed them, if a child got too close, unfortunately, to a candle, a stove, or a space heater, say in their pajamas, they could unfortunately go up in flames, literally. Very sad. And by adding a fire retardant, it slows down so that doesn't happen. Now, there's anything that can burn, you can't stop it from burning, but you can stop it, slow it down. You can't make anything that can burn fireproof. So let's look at this reaction and have some fun. And the same skill you should have and when I say give, that means draw. And let's take a look. How do you do this? Because I know you want your 3 points. Help get a good grade. And you look at a molecule and look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen. That should get your attention like that. And, oh, a double bond. So that's all I see right now. What am I reacting with? Or bromine, Br2, bromine gas, is a halogen, which we abbreviate like that. And remember, X is equal to fluorine, chlorine, that's Cl. I don't think I could print that. Well, let me try. Oh, I don't like the way that looks. Just remember, this is chlorine. You'll learn a little cursive in my class. And bromine and iodine. And what happens? Remember, you've got one pi bond and one sigma bond, and you break pi bonds real easy. You break carbon-carbon single bonds, sigma bonds? No. So I'll break that. And each carbon of the double bond now gets a halogen. So do you break carbon-carbon single bonds? No. Therefore, I have 1, 2, 3 carbons here. Here are my 2 carbons of the double bond. I have 3 carbons. Notice I broke one of the bonds, the pi bond. My general reaction tells me each one gets a halogen. What's my halogen? Bromine. And the bromine is like 1 bond to carbon. So I know there are 4, yes, 4 bonds to carbon, and I can put in my hydrogen. Notice this carbon right here has 1, 2, 3. Bromine counts as 1. 4 minus 3 is 1 hydrogen. This carbon here, right here, has 1, 2. 4 minus 2 is 2, and that's how you do it. Again, look for what's different. Double bond. You break the pi bond, each carbon gets a halogen. You break carbon-carbon single bonds. I started with 3. I better end up with 3 carbons. I did. And the carbons that have the involved in the double bond get the halogen. Now, watch closely. Where you put atoms are very important. Later on, I'll tell you, it can make the difference between life and death in certain situations. This is wrong because the bromines should be on adjacent next to each other carbons. They aren't here. They should have been on this carbon and this carbon like in the answer. So be very careful in my class, and organic chemistry we are, where you put atoms you're adding is just as important as adding those atoms. So that's halogenation. And I'm going to let you try one. And there is one for you to try. Give the organic product or products for the following. Remember, look for what's different. Ooh, I should be nice. I'll show you that. That meaning that. All right, let's do this. Now, if we look at this molecule, the first thing you have to do is look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen should get your attention like that. And if we look right here, it's a double bond. Everything else, carbon, hydrogen, carbon-carbon single bonds. Nothing's going to happen there with this reaction. Reacting it with fluorine gas, and fluorine is the halogen. Remember, X equals, in our case, fluorine, chlorine, bromine, or iodine. And remember, this has one pi bond, one sigma bond. You break the pi bond between the two carbons, the double bond, and I did, and each one gets a halogen. Now, do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5 across, plus a methyl on this carbon right here. So I'm going to immediately write 1, 2, 3, 4, 5 across in my methyl. Now, these two carbons are these two carbons. And notice I broke the pi bond, and my general reaction tells me each one gets a halogen. What's F? Fluorine. And now I know there are 4 bonds to carbon. Yes, 4. And I can put in my hydrogens. And if you have problems doing this, always feel free to, oops, even I have problems doing it. Let's try that again. Pay attention, Dr. White, I will. And remember, it's your job. If I make a mistake, let me know, please. And that's how you do it. Oh, let's try. Let me do one more, then I'll let you try it. And let's look at this reaction. I'll do this, and then you'll have fun too. And if we look at this reaction, what's different? Well, I got a ring, but that's just carbon-carbon single bond. So wait, we have a double bond. And we're reacting with iodine gas, which is a halogen diatomic. X can be fluorine, chlorine, bromine, or iodine. And remember, double bond has one pi bond, one sigma bond. And you break the pi bond between those two carbons, and each one gets a halogen. Do you break carbon-carbon single bonds? No. So I'm still going to have my ring, 5 carbons. The methyl group will still be here. And notice right here are my 2 carbons of the double bond, which are these 2 carbons. Notice I broke the pi bond, and my general reaction shows me each of those carbons gets a halogen. In this case, what is it? Iodine. And I'm done. And that's how you do it. Again, look for what's different. Double bond, reacting with iodine gas, which is a halogen. Break the pi bond, each carbon gets a halogen. In this case, it's iodine. And these are the 2 carbons of the double bond, which are these 2 right here. Do you have to draw the dots and all that in there, the arrows? No, but this is my way of helping you learn this. All right, let me keep this right here where you can still see it, sort of. Your turn. Give the organic product or products to the following reaction. Everybody see the poll I just sent out? There you go. All right, let's do this. Now, the question is, draw or give the organic product or products for this reaction. Oh, we've got a 4-membered ring. That's what that is, not a square. Each bend in a line is a carbon. And how do you do this? You look in the starting material right here. What's different? And I've got a double bond because you look for what's not a carbon-carbon single bond or carbon or hydrogen atom. So I have a double bond, nothing else will react with. Ooh, Br2, that's halogen gas, which I show like this. Remember, that can be fluorine. Redo that. Fluorine, chlorine, bromine, which we have, and it also could be iodine. And you break, remember, this is 1 pi bond, 1 sigma bond. You break the pi bond, and each carbon of the double bond gets a halogen. Now, in this case, do you break carbon-carbon single bonds? No. So I'm still going to have my ring. You call it a square, we call it a ring. I'm still going to have my isopropyl group here. But these 2 carbons here, I break the pi bond like here. And these 2 carbons get a halogen, each one. And what's the halogen? Bromine. And that's halogenation. And I've run this in a research lab. I never worked for a company that did halogenations in bulk, but I've done a lot of the other reactions we'll talk about in bulk. But it's about every reaction I talk about this semester I've run in a laboratory personally. Wow. Now, if you think about the reactions I just showed you, hydrogenation, halogenation, to each carbon of the double bond, we added the same thing. It's called symmetrical. What happens if they're different? You have something that adds like an A and a B. What happens? Well, it turns out that's not a trivial question. Very important question. Notice here, I'm reacting this and adding halogen to each carbon, the same thing. Hydrogenation, hydrogen to each carbon. But now, let's think about if you're adding something different to each carbon. And that's called unsymmetrical addition reactions. Now, it turns out a great, famous, great Russian organic chemist, Markovnikov, solved this problem and came up, which is now called Markovnikov's rule. And if you read the book, and don't write this down, trust me, I'm the teacher. Does that work? Anyways, when an unsymmetrical molecule to form HA or HQ adds to unsymmetrical alkene, double bond, the hydrogen from HA or HQ becomes bonded to the unsaturated carbon atom, one of them in a double bond, that already has the most hydrogens. And you look at that and say, whoa, what does that mean? Well, let's learn Markovnikov's rule. And if you have a double bond, and what we're going to react it with, the first reaction, I should go back to the, hold on. Let's look at this one, where we take a double bond and react it with HX, and usually I'll write it on a test like this. Oops, I gave something away. Where X, in this case, is not all the halogens. It's usually chlorine, bromine, or iodine, either one of those. It's not fluorine, because HF, hydrofluoric acid, is one of the most dangerous chemicals to work with. Quick Dr. White story. Remember, I told you learn a lot of personal things. When I was still a bench chemist, first 2 years I started in industry, then I became the youngest section head in that company. In fact, throughout the chemical industry, one of the youngest. I was asked to work on a research project. And in all my time in chemistry, this was the only time I said, no, I don't want to. You want me to leave the company? I will. And at that time, I'd already made a name for myself solving problems. So they gave it to someone else. What didn't I want to work with? The reactions involved with hydrofluoric acid, HF. It eats right through your skin, right to the bone, and also will kill you. And the person who had to work with it always had one of those hazmat suits on. Whenever he was using HF, about 3 feet behind him was a technician in a hazmat, and the technician's job was to watch, and if something bad happened, which luckily it never did, to get help quick. And that person who did the research almost had a nervous breakdown because of the stress. So that's why you don't see HF in the following reaction. True story. All my stories are true. And now you break, remember, this is a pi bond, and this is a sigma bond, and you'll break one of those, and one carbon gets the H from HX, the other gets the X, and how do you know which? It follows Markovnikov's rule. And instead of you watching me spend the next 30 seconds writing out Markovnikov's name, which sometimes I will spell wrong, I've learned to just put M's rule, but still say his name. That's our way as organic chemists to honor the great work that Markovnikov did, obviously Dr. Markovnikov. Now, let's look at an example. And again, so let's find out how to do Markovnikov's rule. And let's look at this reaction. And the question is, give the organic product or products for the following reaction. And now we look for what's different. Double bond, remember what's not carbon or what's not hydrogen, should get your attention like, ooh, that's better, like that. I have a double bond, and I'm reacting it with H. Ooh, halogen is X. And for this reaction, X is chlorine, bromine, or iodine. I'll never give HF up there. I don't play games, try and trick you. And remember, you got a pi bond and a sigma bond, and you break the pi bond between those two carbons. One carbon gets H and one carbon gets X, and it follows Markovnikov's rule. Oops, almost so used to using cursive, I almost did it on you. There we go. Now, how do you use Markovnikov's rule? Here we have our double bond. Here are the two carbons of the double bond. Do you break carbon-carbon single bonds? No. And therefore, I have my 3 carbons. Now, here are my 2 carbons in double bond. Which one gets this hydrogen? Well, here's where Markovnikov's rule plays the role. You look at the 2 carbons of the double bond, and you count how many hydrogens on each. This has 2, this has 1. And Markovnikov's rule is the hydrogen coming in goes to the carbon of the double bond with the most hydrogens. The hydrogen coming in goes to the carbon of the double bond with the most hydrogens. In this case, I hope you all agree 2 is greater than 1. And therefore, the hydrogen will go there and the halogen goes to the other carbon of double bond. In this case, that. And you know there are 4 bonds to carbon. Halogen counts as 1, so I can put in the rest of my hydrogens. And that's how you do Markovnikov's rule. Let me go over it again. You have a double bond. Here's the reaction. Reacting with HX. 1 carbon, you break the pi bond, one of the lines, 1 carbon gets H, the other gets X, and it follows Markovnikov's rule. The hydrogen from HX goes to the carbon atom with the most hydrogen atoms on that carbon, and the other carbon gets the halogen. And therefore, this has 2, and that's why this got the halogen. And the other carbon gets, the hydrogen, and the other carbon gets the halogen. Now, don't ask me why I still remember this. Well, I know why. He did a great job. When I took my first semester, 2-semester organic at IIT, the instructor I had said, all right, here's Markovnikov's rule. And the easy way to remember it is the rich get richer and the poor get poorer. And we're talking about the hydrogens. The one that has the most hydrogens, the rich, like dollars, gets the hydrogen coming in like dollars, and the other one gets the halogen. And he also said another way of remembering, and don't ask me, this is decades ago. Boy, I shouldn't have said that. But anyways, it was, them that has it gets it. Again, them that has it gets it. And that's how you remember Markovnikov's rule. And I still do to this day. I guess he was an effective teacher. I guess so. I became an organic chemist. He was too. All right, your turn. Give the organic product or products for the following reaction. Use M's rule. Uh-oh, Dr. White made a mistake. Somebody should have caught me. Hold on, let me do this. That shouldn't be there. There. Sorry about that, but still. Let me relaunch this. I'll ask you to vote again. Speaking about voting, Illinois primary is coming up soon. Remember, brave men and women have died so you can vote. You should vote if you're old enough to vote. You can register. It's so simple. You will go online. You live in any of the counties in northern Illinois. You can find out if you're in Kane, Cook, or DuPage, or any other county I'm missing. You should vote. I've never missed an election except for one. That was just a primary for my village, not the state and federal government. And the reason I missed it was I happened to be in Germany and I forgot to get a mail-in ballot early enough, so I couldn't vote. But other than that, every election I've always voted throughout my life, and I will this one. In fact, I just requested a mail-in ballot. It's easier. All right, let's do this. How do we do this? We look at this molecule and say, what's different? What's not a carbon-carbon single bond or carbon or hydrogen? Oh, a double bond. And we're reacting with HX. Bromine is a halogen. And we show halogens by that. For this reaction, X can be chlorine. In our case, it is bromine or iodine. And you break the pi bond of the double bond, not the sigma bond. And each carbon gets something. One gets H, the other gets X. And how do you know? You know it follows Markovnikov's rule. The carbon of the double bond with the most hydrogens gets this hydrogen. The other carbon gets the halogen. Well, here are two carbons that double bond. Let's count hydrogens. This has 2, this has 0. Now you have to use your high-level math skills, which is a greater number. And time's up. Hopefully I'll pick 2. Do you break carbon-carbon single bonds? No. So I still have my 3 carbons in my methyl group there. Now here are the 2 carbons that double bond. I broke the pi bond. Where does this hydrogen go? To the carbon with the most hydrogens. The other carbon gets the halogen. In this case, bromine. And I know there are 4 bonds to carbon. Hopefully I do. Earlier I forgot. And that's how you do it. Again, you look when you're adding HX to double bond, use Markovnikov's rule. The rich get richer, the poor get poorer. Them that has it gets it. We're talking about hydrogens in both cases. And this has 2 hydrogens on the carbon double bond, 0. Markovnikov rule tells you the carbon with the most hydrogens, this one gets the hydrogen, the other gets the halogen. Now, a couple things. Ooh, I can share this with you. You know who the greatest of all organic chemists is, or one of the greatest? Mother Nature. And Mother Nature, and you'll learn this whole semester, has done some phenomenal, amazing organic chemistry. But I do have to tell you, Mother Nature and Dr. White love rings. Students don't. No. Again, Mother Nature and Dr. White love rings, but students don't. Why? Well, let's take a look. And I'll do this one and I'll let you have fun too. And if we look at that reaction, the question is, what's the organic product or products? And you look at this and say, well, I've got a ring. This should be a single bond right here. Hold on, let me clean it up. That's better. And, oh, I got a double bond. That's different. I'm reacting with H and iodine is a halogen. We show that by X. In this reaction, X can be chlorine, bromine, or in our case, or I shouldn't write it or use cursive, iodine. And you break the pi bond. Remember, you got a pi bond there and a sigma you don't. And one carbon gets H and the other gets X, and it follows Markovnikov's rule. The carbon with the most hydrogens gets the hydrogen from HX, the other carbon gets halogen. Wait a second. I don't see any hydrogens. Well, they're there, you just don't show them on a ring. And you've got to count, because you know there are 4 bonds to carbon. If we look at these 2 carbons, this top one has 1, 2, 3 bonds. 4 minus 3 means there's 1 hydrogen there. This bottom carbon has 1, 2, and a double bond counts as 2, which means 4 bonds to carbon. 4 minus 4 is 0. And now, do you break carbon-carbon single bonds? No. So I have my ring. I still have my methyl group. The hydrogens would go there, but you don't show it on this carbon. And the halogen, in this case, iodine, will go here. So let's look at that again. When you have a double bond in a ring, you've got to figure out how many hydrogens are on each carbon of the double bond by knowing there are 4 bonds to carbon. And we did that. The top one has 3 bonds, 4 minus 3 is 1 hydrogen would be there, is there, you just don't show it. And the bottom one, 1, 2, 3, 4 bonds, 4 minus 4 is 0. So the hydrogen goes up here, but we don't show that. Here 1, now it would have 2, so it did get that. And the iodine goes here. Now, if I put and wrote the product like this for this class, oops. These are the same for this class. You can have the iodine methyl in either position, and that's how you do it. And here's your turn. Remember Markovnikov's rule, the rich get richer, the poor get poorer, or them that has it gets it. Amazing the things you remember and the effect teachers have on you. I've had students come back to me and say they still remember this. How many bonds to carbon? if we were face to face, if you had your webcam on, I'd say when you're done, look up and smile. Or if you want, you can also use the thumbs up emoji, but I'll do a poll. Did that guilt work on you? No, didn't. And don't forget, there's an alkene, alkyne practice problem set. And by the end of the day, if I think we're going to get where I know we're going to get to, I'll talk about that. All right, time for me to get to work. If we look at this starting material right here, what's different? What's not a carbon-carbon single bond or a carbon-hydrogen? A double bond. The ring is just carbon hydrogens. I'm reacting it with hydrogen bromide. Remember, halogens are X. X can be, for this reaction, chlorine, bromine, or iodine. In this case, it's bromine. And what happens? Remember, this is one pi bond, one sigma bond. You break the pi bond, and one carbon gets H, the other of the double bond gets X, and it follows Markovnikov's rule, which I abbreviate M's rule. And the carbon of the double bond with the most hydrogens gets this hydrogen, the other carbon gets the halogen. Got a ring, we got to figure out hydrogens. This carbon right here has 1, 2, 3 bonds. 4 minus 3 means there's one hydrogen on there. This carbon here, look out, I'm going Technicolor on you. I just did a generation gap. 1, 2, 3, 4. And are you seeing dots before? Anyways, 4 minus 4 is 0. Now, do you break carbon-carbon single bonds? No. So I'm still going to have my ring. I'm still going to have my ethyl group, CH2, CH3. And now these two carbons, which has the most hydrogens? That one. And that's where the hydrogen. And on this one, the halogen will go. And I'm done. Now, you could have also written it this way. For this class, it's identical. And that's how you do it. Speaking about doing it, it's time to take a break. And I'll see you at 3:50. I'm going to get up and stretch a little. Be back in 5 minutes. let's get going. Now, we just talked about adding an acid, and HX is a hydrochloric, hydrobromic, or hydroiodic acid. That's why I call addition of an acid to an alkene. Alkene is a double bond. Now, let's move on to the next reaction, and that's addition of water to an alkene, also known as hydration of an alkene. Now, the way I have it here, and I'll draw it a better way underneath, if we have a double bond and you react acid. Now, organic chemists use generalization for any acid, H+, because an acid is a proton donor, proton H+. And water, well, that's H2O. Now, let's think of water a little differently and think of water as an H and an OH. That's still two hydrogens, one oxygen, H2O, but think of it that way. And what happens is you've got the pi bond. Uh-oh, sorry about this. Time for my computer to burp at me. Sorry about that. I've got on tap to get more memory for this machine, but I haven't had a chance to do that yet. All right, let's go back to what I was talking about. That's addition of water to double bond, alkene. Double bond has a pi bond, which you can break, and you need the acid, which is a catalyst, makes it go quicker. And one carbon gets the H from the water, and the other gets OH. Now, OH in organic chemistry, and I say both, OH is called the hydroxyl group, and it's like one bond to carbon. And this also follows Markovnikov's rule. The carbon with the most hydrogens of the double bond gets the hydrogen, the other carbon gets the hydroxyl group. And that's how you do Markovnikov's rule with the additional water to double bond. So let's go do one, which means I'm going to do one first. And the question still is, give the organic product or products are the following 3 points each. And if we look at this molecule, what's different? What's not a carbon-carbon single bond or carbon or hydrogen? Double bond. And once I see that, I don't think of anything else. And then I'm reacting with acid catalyst. That's what this is. and water. And remember, water is really HOH, hydroxyl group. And you break the pi bond, not the sigma bond. And of the two carbons, one gets the hydrogen from water, and the other gets the hydroxyl group OH from the water. And this follows Markovnikov's rule, which is the carbon of double bond, which has the most hydrogens, gets the hydrogen, the other carbon gets the hydroxyl group, OH hydroxyl group. So I have this right here are my two carbons. We count the hydrogens. This has two, this has one. And now we look at that and say, do you break carbon-carbon single bonds? No. So I have 1, 2, 3. Here are my two carbons. Notice I broke the pi bond. And the carbon with two hydrogens will get this hydrogen that comes from the water here. And the other carbon gets the hydroxyl group. And you'll learn later on, this is a good way of making what we call alcohols. And there's 4 bonds to carbon. So I know how to put it in. Hydroxyl group here, OH, counts as 1 bond. And that's how you do it. Again, you break the pi bond, and one carbon gets the H from water, the other gets the OH, and it follows Markovnikov's rule. The carbon of the double bond with the most hydrogens gets the hydrogen from water, the other gets the hydroxyl. And it's your turn to have some fun. I hope it is fun for you. Remember, these are how organic chemists using these general reactions make molecules for use in your daily life. Now, I'm using simple ones, and some of them are used in your daily life, but organic chemists at my level do these reactions on very complex molecules. Now we're doing some serious organic chemistry. Really getting into the good stuff. All right, my turn. And if we look at this molecule right here, what's different? What's not a carbon-carbon single bond? Carbon or hydrogen should get your attention like that. And the answer is, oh, a double bond. So all I see in there is a double bond, nothing else will react. I'm reacting with acid catalyst, H plus. And in real life, we'd use an acid like H2SO4, sulfuric, and ones you don't know about, but there's toluene sulfonic acid and methane sulfonic acid. And we have water. Remember, water is HOH, and this has a pi bond, which we can break, and we do. And the two carbons, the double bond, one gets the H from the water, the other gets the OH hydroxyl group. And it follows Markovnikov's rule. The carbon of the double bond with the most hydrogens gets the hydrogen, and the other gets the hydroxyl group OH. Now, if we look here, here are my two carbons double bond. This has two hydrogens, this has zero. Which one is more? Hopefully I'll pick two. Do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4 across, and I still have that methyl group on this carbon. And here are my two carbons of the double bond. And the first one has two hydrogens, which means the hydrogen coming in will go there. And the second one gets the hydroxyl group. And I know there are 4 bonds to carbon. OH is 1 bond to carbon. That should be a 2, 2, 3. Can't see it, but that's the number 2. And that's how you do it. Now, let's see if you're up to a challenge. And here's the challenge for you. Give the organic product or products or the following. Remember, count the bonds and figure out how many hydrogens on those carbons. Hint, If you need more time, give me a thumbs up. I guess everybody's done, so I better get to work. And how do we do this? Well, we look at the molecule and look for what's different. And we see, remember, what's not a carbon-carbon single bond or carbon or hydrogen should get your attention. And the double bond got mine. Reacting with acid catalyst, H plus water. Remember, water is HOH. You break the pi bond. One carbon of the double bond gets the H, and the other gets the OH, and it follows Markovnikov's rule. The carbons with the carbon of double bond with the most hydrogen gets the hydrogen, the other gets the hydroxy group, OH. The rich get richer, poor get poorer. Them that has it gets it. And if we look here, a ring, we got to count bonds. 1, 2, 3. 4 minus 3 is 1. 1 hydrogen there. This carbon, 1, 2, 3, 4. 4 minus 4 is 0. Do you break carbon-carbon single bonds? No. But you do break the pi bond. The hydrogen goes to this carbon, but we don't show it. But the hydroxy group OH goes here. And you could have also drawn it this way. And that's how you do it. And let's move on. Now let's talk about alkynes. And I'm going to skip this, but the important thing is a triple bond has 2 pi bonds and 1 sigma bond. A triple bond, as it says here in red, has 2 pi bonds, and as you've learned, pi bonds react. So let's look at the next reaction. Now, this is hydrogenation of an alkyne. Alkyne, triple bond. And if I react it, now it has 2 pi bonds. If I react it with hydrogen and a catalyst, where the catalyst can still be platinum, palladium, or nickel. I should have written it, printed it. And now you break, each time you break a pi bond, a carbon of the double bond gets a hydrogen. 1 pi bond, 2 pi bonds, which means each carbon of the double bond gets 2 hydrogens. Now, notice we add 2 moles or molecules of hydrogen gas. Organic chemists are lazy. I don't want to balance this, so I'm going to do this. Bracket, the letter X, and the letter S, close bracket. And this means you have excess hydrogen. Another way of saying it is you've got all the hydrogen in the world that react with anything hydrogen can react with. So that's what the excess means, because you need extra more than a double bond because you've got 2 pi bonds. If we look at this reaction, what's the organic product or product of the following? We look here, what's different, a triple bond? What are we reacting it with? Excess hydrogen. Remember the bracket X, S, closed bracket means you got all the hydrogen in the world that can react with anything that hydrogen can react with. You don't have to balance it. Now you have a catalyst. Remember the catalyst is nickel, platinum, or palladium. Doesn't matter which order we write it in. And now you have 2 pi bonds So each carbon of the triple bond gets not one, but two hydrogens. Do we break carbon-carbon single bonds? No. So I have 4 carbons. Over here, I'll end up with 4 carbons. Here are my 2 carbons of the triple bond. Each get a hydrogen. I know there are 4 bonds to carbon, and I can fill in the rest of the hydrogens. Again, break the 2 pi bonds. Each carbon of the triple bond gets 2 hydrogens. And it's your turn. And once in a while in a problem set, I'll forget to put excess. If I do, let me know. Same thing on a test. I just, at my level, we're so lazy. Sometimes we don't even put that there. Your turn, give the organic product or products you're following. All right, it looks like everybody's done, but I'll give you another 15.7 seconds. Go. That's about that. All right, let's take a look at this. Look at the molecule, look for what's different, what's not a carbon-carbon single bond or a carbon or hydrogen atom should get your attention. It did. I have a triple bond. I'm reacting it with hydrogen and I have excess, meaning I have all the hydrogen in the world, and platinum is a catalyst. And this could have had palladium, which it doesn't, or nickel. And you break the 2 pi bonds, and each carbon of the triple bond gets 2 hydrogens. And you break carbon-carbon single bonds? No. 1, 2, 3, 4, 5. Here are my 2 carbons of the double bond, triple bond. And each one gets 2 hydrogens. And now I know there are 4 bonds to carbon. Oops, don't need that extra 2. And I'm done. All right, let's continue on. Let's do one more reaction. And that's halogenation of a triple bond. Alkyne, triple bond. Triple bond, 2 pi bonds. React it with halogen gas. But now, since we have 2 pi bonds, we're going to need more halogen. Since I don't want to balance it, I'll put bracket, letter X, letter S, close bracket. That tells me I have all the halogen in the world, and X can be fluorine, chlorine, bromine, iodide in this reaction. And now, since I have 2 pi bonds, each carbon of the triple bond gets 2 halogens. And that's how you do it. Again, 2 pi bonds reacted with halogen gas. Each carbon of the triple bond gets, which is no longer because I broke the 2 pi bonds, now gets 2 halogens. Now, I'm going to do something I normally don't like to do, but I want to get the lab in. I also want to finish this. So I'm going to test you on something. Why don't you work on that reaction? Normally I do one, then you do one, but I want to get the lab in and get you out on time. And so why don't you try this on your own? Excuse me. All right, I think everybody's done. Let's go ahead and do this. And how do you do this reaction? You look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen should get your attention. Oh, a triple bond. And we're reacting with excess bromine, which is a halogen, and a triple bond halogen gas. You break the 2 pi bonds, and each carbon of the triple bond gets not 1, but 2 halogens. Do you break carbon-carbon single bonds? No. So I start with 1, 2, 3, 4 carbons. I better end up with 4 carbons. Now, here are my 2 carbons of the triple bond. I've broken both pi bonds, only one line instead of three, and each one gets not one, but two halogens. In this case, it's bromine. And I know there are 4 bonds to carbon. And I'm done with this. Bear with me 1 second, maybe a couple seconds. And it's lab time. It's time for a lab. And today's lab, don't forget the hand in the lab you did on Tuesday. This one will be due next Tuesday. Today's lab deals with distillation. Thumbs up, people. Everybody see purification by distillation on your screen. Thank you, Jordan. All right, and Jimmy too. And everybody else, thank you for coming to class. All right, what happens if you have a mixture of a couple liquids or 2 liquids? What if you make something that's liquid and it's not pure? How do you purify it? You use what we call distillation. And this lab, you'll learn about distillation. And compounds that you heat up that are liquids will boil. And when you boil something, you get inside the liquid. Oh, by the way, warning, I'm going to do some artwork and feel free to laugh, but not so hard that you hurt yourself. If I have a beaker, say of this water, and I heat it up on a hot plate, there's with a cord to electricity, all of a sudden you'll see bubbles come in there. And what's in the bubbles? The gas of the liquid you're heating up. And if it's water vapor. That's what we call gas. And they come up to the top and release the water. And that's the pressure of water coming up, vapor, gas, and you have the atmospheric pressure. And when those two are equal, that temperature in the liquid is called the boiling point of that liquid. And most of you probably know the boiling point of water at atmospheric pressure, sea level, which is Chicagoland, is 100 degrees C to 12 Fahrenheit. Now, the bubbles rise, and if you do this with an organic compound, the vapor will go here. And if you have 2 things that have different boiling points, you can separate it. One will boil first, and its vapor will go up. And if you ever take a pot, which you shouldn't do, and you leave it on a stove too long, what happens to the water? It's all gone. So this is important. Now, how do we do this? We do this with a distillation apparatus. And a distillation apparatus consists of what's called a round bottom flask, this distillation head, then there's an adapter for a thermometer, or as if we were at ECC about 3 or 4 years ago, maybe a little longer, we went to thermocouples, electronic thermometers. And then we have what's called a condenser here and the condenser adapter. Now you put your liquid in here. Now, a couple of things. When you boil something, and this is important, pay attention. Inside, whether it's a round bottom or anything, you get these bubbles right here. If you do it in metal, the metal is very rough, and that helps form little bubbles. If you do it in glass, like a round bottom, it's very smooth. And you have to add what we call boiling chips or boiling stones. That's a P. And this gives a rough surface for the bubbles to form. Because if you didn't, these big bubbles would form and burst and stuff would come over and you wouldn't get a good distillation. Now, we use what's called a heating mantle, which is like a hot electric blanket, but gets very hot to heat this, and you have electricity and a controller here. And bubbles come up and the vapor, you have your boiling chips in there, and it rises here. These are all together and comes here. Now, condenser has an inner tube and an outer tube that is separate. And water comes in here and comes out here. And water always comes in at the bottom. Why? Because it fills it up, this outer tube, which will condense the vapor that's coming over and cause it to be a liquid that will be coming down here, and you could collect it. And when you heat it slowly, if you have a mixture, one will come over, distill over, boil and distill over the other. Now, if you put the water in at the top, which you shouldn't, this will never fill up. You put water in the bottom. Next, another important safety feature is you never fill a round bottom to more than 2/3. And why do we do that? Well, have you ever been at home and you're cooking something where you're going to put it in boiling water, like rice, noodles, or whatever? And do you put the water all the way to the very top of the pot? No, because it boils over. And the same thing would happen here, and you wouldn't get a separation to purify, make pure liquid by distillation. It's show and tell time. Now, when I was in grad school, we used very tiny in the lab. We're here at ECC. We have bigger ones. This is called bantamware. This one is 50 milliliters. I got it on eBay a long time after I left graduate school. But this is for when you do research on very small amounts of material. And here's a distillation tube head and everything together. Here's the condenser, water in, water out. And these are called ground glass joints. And if you notice, I've got a male, female, that goes like this. Now, what I don't have at home, but if we were in the lab, you'd put vacuum grease on here to lubricate this so this doesn't get stuck. And then water in and out, and you'd heat this up, and vapor would come up here. You'd have a thermometer in here. I don't have one. And would come down here and you collect it. Now, this over here allows you to pull a vacuum, when you pull a vacuum, which we won't do, and we wouldn't do at ECC, you have, by the way, now you know I'm an organic chemist. I got this at eBay too. When I was in grad school, I had 3 of these. These were my friends because I did a lot of distillations. In a chemical plant, I've managed distillations of a couple 100,000 pounds. But anyways, what you would learn in the lab, most of the lab, if we were in a lab right now, you learn how to set this up. Now I have, and I'll let you watch this on your own, 2 YouTube videos that you should watch. Now, another important thing is you never let a distillation round bottom flask go dry. Just like in a house, you don't want a pot to get dry because it could start a fire, or in this case, could blow up in a lab if you had certain things that were very heat sensitive. So the way I had this lab set up, it was always, we have more in the lab, in the round bottom, than you would ever have to take out, so it won't go dry. Now, how do you know what the boiling point of the liquid you're distilling and purifying? Well, when the temperature is level, that's the boiling point. And this one, I show you the procedure, how to do this in the lab. You look at the video, and fortunately, I don't have it, you won't do it at home. And when it's about level, about the same, it may vary a little. That's the boiling point. And the lab, if we had done that, you start heating it up and you collect it in a graduated cylinder. And at 2 milliliters, you record the temperature, 4, 6, 8, 10, 12, and 14. We have 30 in there. So when you're through, you're still have 16, so it doesn't go to dryness. So remember, we never fill it more than 2/3 or we'll boil over. We put boiling chips in there so it won't bump up and boil over. I actually saw the aftermath in a research lab, and the guy was an idiot because he forgot to put the boiling chips in. And this wasn't a teaching lab, that the thermometer, when it bumped, went flying straight up into the ceiling. And you know how they have the ceiling tiles? It's stuck right in there. He was lucky worse didn't happen. But anyways, please watch these YouTubes. Here's the data, and here are the questions for you to answer. And I think I'm done. And remember the title of today's lab and question 5. That's my gift for you this week. Another one, remember for question 5, the title of this lab, that will help you out. Now, important thing, we're done with the alkenes, alkynes problem set. It's summer and we're moving at a good pace. So on Monday, I will start out doing the practice problems with you, and you should do it before I do. Hint, I'll help you get a good grade, especially on test 1, double hint, and I'll do that on Monday. Don't forget, on Monday after class, I'll teach, for those who want to stick around, take about 15 minutes, 10, 15 minutes, about 12, 15 minutes, the method I developed years ago, and it works real good. I've even had people not in chemistry, but teach their 10-year-olds the method and help them in grade school to overcome test anxiety, go from C's and D's to A's. I'll do that at the end of Monday's lecture, but I will cut that out of the video. Don't you like my special effects? Not really. But anyways, I'll cut that out of the video. If you can't come to the class, come to my office hour, make arrangements with me, and I'll help you out in private on Zoom. And with that, don't forget, this lab is due next Tuesday. The lab we did this Tuesday is due today, or even tomorrow morning is all right. And guess what? You survived a whole week of organic chemistry with Dr. White. Party hard. We're not really do the practice problems. And with that, I'll say Gangason. Goodbye. I'll see you on Monday. Have a nice rest couple of days. Don't forget, do the problem set, alkynes, alkenes for Monday. Bye now. Thank you, everybody.